Okay. Good evening, ladies and gentlemen. Who has been at MIIA events before? So I know there's a few. It's always great to see new faces as well. So that's awesome. On the I think there might be more people trickling in here because on the meetup I think there was about 70 people as well. So, but it's a good crowd here. We've got food there. There's drinks there. If you haven't been to this facilities before, there's also the toilet and stuff is down there. So if you go out, it's just straight in the corner. And we're gonna quickly start today. So let's quickly look at the agenda. Okay, so as you can gather from that, I'm Jacques Ludik, so what I will do, what we planned for tonight is more or less the agenda. We're going to talk about AlphaZero. Who doesn't know anything about AlphaZero? Okay, cool. Who has actually played with it a little bit? No one. Good. So that's good. So you can show a little bit. We're going to keep it still high level, but Benjamin is going to do a proper introduction, so I'll need to quickly introduce Benjamin soon. So that's going to be the heart of today. So what we want to do first is just obviously say thanks to our sponsors, and I will quickly talk about that very briefly. But the next item there is just to talk about MIIA, just quickly what we're doing, what are some of the upcoming events. You can also go to the website, the events website, and you can get more information. And then we're going to go straight into the AlphaGo stuff. And the way we want to organize it, we actually want to keep it very interactive as well. So, but we'll start off with a proper introduction to just the deep reinforcement learning. It's actually deep reinforcement learning and Monte Carlo search. But Benjamin is actually going to go through that and how it works. And it's actually going to trace a little bit of that history, where it all started, and then go into AlphaZero, which is really is actually fantastic stuff. And then we're going to do a demo, and I deliberately call it the Alpha Connect 4.0 because with AlphaZero, the latest version, that you can actually play Go, chess, or various games as well. So obviously this is now specifically a Connect 4. And we'll keep this interactive. We will actually involve you in terms of playing AlphaZero for that game. So let's see if we can beat it. So I don't know how well you trained it, but we'll see. We actually had a game earlier today, and we thought we're going to beat it, and it still won. So I think it's not too bad. So, and then what we want to do, we want to have an open discussion after that. And just talk about, I think there's a lot of hype around AI and all these types of stuff, and I just think yesterday or the day before, I listened to, I think it was Elon Musk just talking about talking about AlphaZero and using this as an example of how the exponential growth of AI and the path to super digital intelligence and that type of stuff. And I think what we also want to do here is just to also portray a kind of more accurate understanding of what's happening here. There's some strengths and limitations. It's very good engineering, but I think we're very far from super digital intelligence. But obviously we need to be careful and think about it. The one thing Elon Musk specifically said as well, that the narrow intelligence obviously doesn't pose a risk. So he's moved on to all of that, so that's good. We know regulation is important with weaponry and self-driving cars and all those types of things. But I think let's have an open discussion, just talk about these things. If you've got interesting thoughts or questions, we can have people in the audience even trying to address that, but we'll do our best. So that's part of being interactive around this event. So without further ado, so I first want to thank Rise Cape Town. So obviously they're providing us with the venue. We've had events here before. That's been great. And as a matter of fact, there's another collaboration next month where MIIA is also participating. You will actually see it on the MIIA events calendar. And it's actually talking about the pitfalls of machine learning and also the opportunities. And we're going to have an interesting panel participating in that discussion. So there's going to be a panel discussion and also interaction with the audience. That's in the morning actually, 10 to 12, so it's a different time slot. Normally the MIIA events is in the evenings. There's also an event in Sandton. We're looking at having that at PwC at their new building in Midrand. Actually not Sandton, it's Midrand. And we'll have a similar kind of thing, panel discussion and talk about that. If you're interested to participate in future events as a speaker or any other speaker or panel discussion and so forth, you're most welcome to email me or just send an email to info@machineintelligenceafrica.org. So I know there's guys that we talked about the audience that's got a lot to share. As a matter of fact, you've been at NIPS last year, end of last year, NIPS in 2017. Yeah. So, and maybe to share a bit about that whole experience and so forth is also good. Okay, so, and I also want to thank Cortex Logic. It's actually my company that's really focused on generating, providing an AI engine for business. And so maybe what I will do is just to get out of this presentation briefly. I just want to go to Cortex, and I will go back to this one here as well. So you can get more information about this. Obviously, we want to thank you because we helped sponsor this as well. But here on this particular website, you can find more details. If you want more information, you can also email, and we can provide. We are also hiring. You can go to careers, and you'll see there's positions available. We're in a very exciting journey, trying to build a world-class AI business on the African continent. My previous AI business was called Season Systems, and we sold that to General Electric. That was the first AI company sold to a multinational on the African continent and stuff. So there's a track record of things here. My personal massive transformative purpose is around how to shape a better future in the smart technology era. So even if you look at MIIA, it's all about how can we transform Africa using smart technology. So people like you that's interested in this space, has got skills and energy to help create a better future. Well, this is why we have these kind of events. So how can we work together? So anyway, so this is just a vehicle. MIIA is another vehicle. There's some other companies here that's represented that's doing that. So for me, it's about collaboration, and also we want to leapfrog here in Africa. We don't want to be left behind. So it's very important to network together critical resources to make a difference. And the countries in Africa need people like us. With all the smart technology, we talk about the fourth industrial revolution. So when I say, we don't talk about the smart technology era, it's kind of my description for the fourth industrial revolution. Is just making it more generic. And it's very disruptive. And we typically, I think there's a saying around this, it's not this, the big fish that eats the small fish. It's the fast fish which eats the slow fish. And that slow fish could be corporates. So it's a very disruptive time. Great opportunities. It's like with blockchain and AI, it's like just before the internet, like the Wild West. There's so many opportunities. So we can make a big difference here in Africa and be world leading in terms of what we do there. If we're innovative, we should be confident. That's why I'm excited about these kind of events like the Deep Learning in Indaba, Google DeepMind, plowing back, which is awesome. There's some South African representatives that was at the Deep Learning in Indaba. I don't know, who was at the Deep Learning in Indaba last year? There's a few guys there. We're going to have that Indaba event in September. It's also on the MIIA website at Stellenbosch University. And they're expecting not 300, but 600 deep learning practitioners or people involved in this area. So this thing is growing, and it's one of the biggest events in the world around this. Well, NIPS is a lot of people there, but as a week-long type of Indaba, it's fantastic. And there's a bunch of other things, conferences where MIIA is also a partner, like the AI Expo, that's happening in that same week actually in September. And well, there's many other things. But so anyway, so you can go there. But so what I wanted to show just quickly, if you go to the MIIA website, this is the events page. And there's a blog page that shows more about what happened last year and also what's happening going forward. And then you can go to the partners one and so forth. But I think this one is interesting in the sense that it's showing the growth path and all the type of events. And here's the AA Expo I referred to, deep learning in Java. But there's a bunch of events that's coming up as well. So that's the panel discussion I talked about. That meeting on the Sandton in Midrain. The deep learning in Java. We'll also put this on. We've got this on this page, but there's a dedicated website there. The deep learning in Java X, and that's a Western Cape thing. So we've got people from UCT, Stellenbosch, and just the Western Cape communicating, and it's like a mini deep learning in Java, but just a day focused on various things. So welcome you to join if you want. Okay, yeah, but anyway, so here you can get more information. The deep learning in Java, Stellenbosch, that's a big event. We'll put more stuff up here. So yeah, so anyway, you can read through it. There's also Saturday, there's people preparing here. I'm more a Python fan, but R is also important. And there's a tool, there's actually on Saturday, R day, it's coming. So it's in March here. And I saw some people participating, preparing for that. Anyway, okay, so here we are. So without further, so I just want to say, so there are these kind of articles that this one describes a little bit of what's happening, so it gives you a little bit of background. So you're welcome to read through it and so forth. And this is just talking about last year. So this is like it's a long blog, but it talks about all of that. This is also available on the MIIA blog site. So this is if you want to know a little bit more, you're welcome to go through these things. Okay, so without further ado, so let's get Benjamin on. Yeah, so there's some other things about MIIA, but I think we'll start a bit late, so I'm going to start straight away. So Benjamin, where are you? Yeah, okay, good. So Benjamin, he just finished his master's at UCT Electrical Engineering. He actually worked before, then went back because he wanted to do his master's. He can maybe more talk. He actually did some aircraft tracking using, was it machine learning as well, but vision techniques, all sorts of things, real time and stuff. But he's one of the key senior software engineers and machine learning guys at Cortex as well. So it's great to have him finally also participate here. So what we will do is you'll start with the presentation and then go into the demo, and then we'll have that open discussion. So go for it. You may maybe speak up. I don't know if we've got
Go, I don't know, I'm sure a lot of you have at least sort of seen what a Go board looks like. There's basically black stones, white stones, and you play on the keys. I myself played probably about 1.5 games of Go, so
you're not an expert, but that's why we need the audience.
Yeah, so there are, I'll highlight one or two of the important rules that come up, but basically you try and like capture areas of the board. So quite a big breakthrough came from Google DeepMind's group that they built the first computer program to beat a human expert at Go in 2015. Then they did a bunch of like iterations. They changed the network, the neural network structures, and played around like that and got some better improvements. And then they beat the first announced down professional, Lisa Dole, who's apparently one of the best Go players of recent time. And then they developed AlphaZero, and that is what a lot of like the recent news has been about, because there they use nothing more than the rules of the game to train their computer program, and that was able to, after 40 days of training, was able to beat their previous-based AlphaGo. So that was what the big noise was essentially about, is taking all human data out of it, just giving the system the rules of the game and say to it learn. And then now what they've done is they've created AlphaZero, and basically like insert your own game, provide rules for a game, and train it up, and it'll be able to play the game. Now I'll explain a little bit in detail what games are allowed. I mean, not all games fit the profile for this kind of technique. And then we'll see how Alpha Connect 4 plays against us as a combined brain. Yeah, so these are the properties of the game that these systems can be trained on. So it must be discrete, so the moves are like countable moves. Deterministic, so that means that like if you play a move, say the state of the world is the board, you play that move, the board changes to that action that you made. So it's not like you play a move and then there's a random dice roll and you get 50% of the move you wanted to play. So the control action by each player is reflected in the state, so that's deterministic. It's a game, so it's like competitive, one player against the other. And then also perfect information. So everybody who's playing can see the full board. There's no hidden cards or these sort of things. So,
would backgammon apply?
I don't really know backgammon, but I was there dice.
Yeah. Backgammon would apply.
It's
rules. It's dice. Yeah, it would apply.
I don't know what your control. Like I'm thinking like your control authority is deterministic. So if I push the lever to stone on that vertex, then the stone must be there. I don't know what happens when you involve dice. I don't know if you can run. You'll see the simulations that you run down this tree, and if there's non-deterministic behavior, I don't know how the search down the tree from one state to the next would play out. Yeah, so that's the field of market decision processes. So these games are actually like a special case, I guess. So if you do have partly random behavior and it's only partly under the control of the player, then the keyword to put into Google is market decision processes. See how you can continue from there. Yeah, that's what I'm okay, so I'll briefly explain how AlphaGo works, the one that was trained using human data, and then I'll move on to also briefly explain how AlphaZero was able to take the human data out of it. So the way it works is there's sort of two parts to it. There's or three parts. There's two policies: a value policy and a decision policy. And then there's what they call a Monte Carlo tree search. So I'll just briefly, because I've got this visual here, I'll just say what the tree search is. So it basically is these games from, let's say I'm in state like 5 black, or let's say it's tic-tac-toe, and there's 1 X in the top corner, then I can easily search, there's whatever 8 other moves that I can make with my circle, and I can go and say I want to put a circle there and simulate the game all the way down to the end. So Monte Carlo tree search basically says if you've got policies on how to make those decisions, and you don't have to search the whole tree, you can kind of guide your search down the tree. So the policy network, this is, in this version of AlphaGo, was a convolutional neural network. Took in the bottom there, a board representation of the game. So the way they actually did it was a binary matrix. So say player white has ones or zeros, and 0 and 1s, and 1's marking where the white stone is, what stones are, and player black has also 1's marking where the black stones are. And then they also inputted a history of the game, so the previous 8 boards. That's because some of the rules are such that you're not allowed to return the game to a state that it was in. So they had like what they said was like a sort of retention mechanism by embedding 8 previous states of the game. And then they also had another sort of slice. This board is 19 by 19, so that another 19 by 19 matrix layer, if you want to think of these things as stacked on top of each other, which represented whose turn it was. Yeah, so they had like 17 by 19 by 19, input vector, and they push that through a convolutional neural net. So that's what they played around with different network structures to get the different, it was like a lot of the iterations and improvements. Push it through, and then out pops move probability. So the output of the network is this vector of all possible moves and a weighting on how good that move is. I'll explain how they train that up later. And then there's another network takes the exact same input, and the output is, are you going to win the game or not? And then, so the way they trained AlphaGo, they took a data set of human experts from, I think there was like an online Go playing service, something like this, maybe some recorded games. And then they trained up the policy network. So they said, this is a board, create that representation, shove it in, what did the experts, what expert move did they do, and train up the network until the network gave high probability to the moves that the experts gave and low probability to the ones that nobody made in that data set. And then what they did is they took the policy network and they made it play games against itself. So both players of the game would just do the move, the most probable move, or they would draw from that distribution of outputs. I'm not exactly sure, didn't really see the details there, but you would basically guide a move by that output of that policy network. And then that would create a bunch of games where you would have a player and then who won. And at each time slice in that game, there's a board, and then you know who won because you ran the full simulation. So then you take that and you train your value network. Because remember, the value network needs to say, from this board configuration, are you going to win or lose? Now you've got a bunch of games, massive data set of simulated games with, at each stage of the game, you've got a board position and you know who won. So you can train up the value network. And I'll explain briefly. So I already explained very briefly how Monte Carlo tree search works, but each node is the state. Each arrow is an action that you're going to take to get to that state. And the Monte Carlo part, so like the simulation part there is represented in this way. So you try and explore the tree, and when you get to a point where you're not sure how to score, is that state a good state to be in or not, a very naive policy would be just to randomly explore moves and play the game till conclusion, and maybe run like a couple of thousand of those or more, and you're just randomly exploring from that game state what happens if you play the game onwards. And let's say you win, out of the 1,000 you win like 3 games, then you can be like, well, if I'm in this game state, there's a low probability that I'm actually going to win. But that's listening to maybe a dumb policy, so that's not very informative. And then you trace that back up, and then you make the decision on where to go. So how that relates to AlphaGo. So you take the two networks basically allow you to make the search tractable. So what that means is we don't have to search the entire breadth of all possible moves, because we can already ask the policy network, I'm in this board state, which moves do you recommend? And the policy can say, well, basically this is the only move that's worth exploring. So the breadth is cut down, so you can make that move more. You can search basically only good moves according to your policy, obviously. So that's why they trained it on human experts, and so they had a good policy to go by. And then the depth can be also, you don't have to explore to the end of the tree, because again you've got a value network that says from this board configuration, are you going to win or lose? So if you can already figure out with just one pass of that network if you're going to win or lose, it's like, do you need to continue exploring this tree or not? So basically it's search with trained up policies.
So do I get it right? It's the value network runs to the end, and that determines the value that if you were to run to the end, how useful would that move with a single move
No.
to F3?
From that state, are you going to win or are you going to
So it
lose?
determines the value of that state.
State.
Yeah.
So
So like-
by running to the end, yeah.
So if it's like tic-tac-toe and there's like, it's your go and you're going to hit the last one in the row, then from that state, it's like high probability that you're going to win because you've got a winning move, if you know what I mean. So it takes in the input is the state of the world, and output is winning, losing, or drawing. In Go, I believe you can only win and lose. Yeah, and then so then how were they able to?
You got to explain that image.
I don't know if anybody knows some of these like useless machines, but this one's kind of cool. I've got like one useless machine with another useless
Who's winning?
machine. So maybe that's. So yeah, so AlphaGo 0 is now taking the initialized policy network out of it. So we don't have a data set to train a policy at the beginning.
I was going to say probability of winning the game versus the actual winning the game. So there's play 1,000 games, and if somebody plays that sequence of moves, that means one to win, even though 1,000 variations would be winning. Like, so
Are you talking about the value
the
network?
value network, yeah. How do you define the value network? Is it a probability or is it?
Yeah, it's a score between 0 and 1 of whether you'll win the game.
Okay, so it's not that the player could, if he knew, play that route to the winning
No.
game.
So it's just saying I've had a bunch of games. I've had like all the boards lined up that I ever saw.
Yeah.
And this game was part of game 3, move 10, and the person won. That's all that was put in, was the input board and then the results of the game. So it wasn't anything like it was this board followed by that. Well, I guess there is the retention in the 8 board, so yeah, it's kind of more than maybe one turn in there. I hadn't thought of that. But yeah, it's just from that state, what was the final outcome? Yeah. So now, how do we get rid of the humans?
It sounds terrible, by the way.
So they took out the expert data sets. They changed the neural network, both the policy network and the value network. They changed those into a residual network, which has like these long connectors, which basically allows you to have a lot of layers and still train relatively quickly. And they combined the network into a single network with which they split out into 2 gates. I don't know if you might have a diagram of residual networks that can do that. So basically you have the same input, because they both take the same input, run through similar layers for some part, and then they split it out, and then they have 2 gates. One which is just the output of value when lose score, and the other one is the distribution over moves. Okay, so what do? They start, so P and V are representing this combined policy and value network. And they take those both the weights in those neural networks are initialized randomly. And so let's say we have a game. We still direct the search using this random initialized policy and value networks. And we follow the search, and we do the exact same thing, and we find a move, and we take that move, and we play the game, and we keep playing the game until we get to the end of the game. And then we have a winner and a loser. And I mean, yeah, so then what they say is they say, well, let's say from to come to move 1, from the beginning of the game to the first move, what did we do? We had a neural network, then we had a Monte Carlo tree search. Can't we just train our neural network to go from beginning of the game straight to that first move? So they don't have to search any space. So what they do is then they say, well, we'll create a new policy network. And this one is we're going to force it to give an output of what the output of the first one combined with the search gave. I'm seeing blank faces. So and this is the part, I think it's kind of clever. So what they said is, they said, we have a network, you put it in a game state and you get a distribution over moves. And we use that to guide our search. But now at the end of the search, all you've done is the search still gives you a move at the end of the day. And then all they're doing is they're saying, well, let's just train our network to give us that move immediately without having to search for it. That's pretty cool. So we can train a new network, and you run a game again. And again, you get this like, say, call it like a slightly dumber network. Combined with search gives you a good move. And then you say, well, actually, why didn't I just get that move straight away? Why didn't I have higher probability distribution of that searched for move, which took me a lot of computation, straight off the bat? So they say, okay, well, we'll just train the thing again and create a new policy that now gives you the better one. And each time you just keep going through until your neural network starts producing actual proper moves, because they are now matching the ones that on the previous iterations you've actually had to do hard computations for. You've had to search through a bunch of states, bunch of ones, and figure out, was that a good move or a bad move? And so they just kept going. And basically, the way they don't want to talk, that they basically saw this, is that they were like looking for better and better training data, and they just realized they can just generate their own training data and the way it goes. And you do the same thing for the value network. So each time you played a game, you have a board and you score it. Yep.
Sorry, going back 2 slides, you say that randomized initialization, so your value network is randomized for every point in that whole search, and you're improving that training as you go through that,
yes.
that process.
So
It starts random.
The neural network is just initialized with random weight. So we put in a board for that first one, and then I reckon the move distribution over moves is going to be like completely random. If an expert looked at it, he would say, no, I don't agree with any of those peaks or whatever in that distribution, or it just looks like noise, I'd imagine. And then but you still listen to it, and you run the search to come up with something slightly better than that, and then you say, okay, well, I want to get there in one step, and you reweight so that your network would have given you there in one pass. And you do the same for the value network.
Just, would you need that randomness, or if you just need to prevent yourself from reaching the local minimum?
Yeah, I kind of looked for stuff like that. I didn't.
It's just for
I
the
don't know
start.
what the guarantees are about why, like, some kind of like the one comment that I did come across asking why, like, because a lot of reinforcement learning is they have, like, when they try and do this kind of like train yourself mechanism, is they often have like quite unstable results. And a comment was made that it's the tree search that actually allows it to not become unstable and get somewhere. Because the tree search is real computation looking for a real answer. It's a method of finding a better answer. So I guess it's guiding enough that allows it to produce better and better networks. Yeah.
So does the network basically just memorize what it finds?
Yeah, it tries to be able to say that everything that it has seen before, it can produce that output. So, like the normal images of like cats on the inside, it must give it label high probability that it's a cat. I mean, it doesn't memorize every image there, but the weights are tweaked in such a way that's what it pushes out in simple terms.
Who's not familiar with neural nets? Because I think the principle here is everything is really stored in the connection, the weights of the connections. So basically all that's happening here is the combining that obviously the policy and the value information in that information around what's good moves and what's the value is effectively stored in the weights of the connections. So, and if it starts off random, typically randomize it between -0.5 and 0.5, but then as you continue training this, it actually gets better with it. So it's like any other typical neural network. It's just learning policies and values. Well, that's what it is.
Yeah, but you can't get it to just memorize it. If you get the
If you had like a big lookup table,
it's simply just going to be a massive.
The problem is the possibilities, because then otherwise it's like Deep Blue of chess. With Go, you've got too many moves. You can't memorize it. That's actually what you try to do with neural network is not to memorize. You're trying to make sure it generalizes. And to make that happen, you've got a training set, validation set, test sets, and you want to make sure that's how backpropagation works. Is to make sure that it can generalize on unseen data. So you test it on validation, and then you can look at your test data as well. So it's the same kind of thing that applies even with deep reinforcement learning. Deep reinforcement learning, you've got penalty reward. So you've got a cost function, and it says, are you making the right move or bad move? So it just penalizes you, or it's okay. It pushes you in the right direction. But all that information is stored in the connections, in the weights. In your brain as well, in the synapse, your brain. This is where you store information. It's also timing. Well, there's a bunch of things there, how it works, but yeah. Sorry.
and then, yeah, so that's how AlphaZero, in this case, it was playing the game of Go. This is the result that the DeepMind group published. ELO rating is like a rating on how good one player is versus another player. So, like it's basically like if you beat somebody with a higher ELO rating than you go up a certain number of points in the scale. That's how they do it. Originally made for chess, but applied to all of these kind of games. So you can see it starts off like terrible. I guess it's like random play, and then it ramps up pretty quickly, and that was the first result that they cited. Like under about 3 days or something of training, they were able to beat AlphaGo Lead, which is the one that beat Lisa Doll, and then they beat AlphaGo Master. I think in the trials they beat it like 100 to 0.
Yeah.
So really convincing you. Yeah. And that's the results. And then this I thought was quite interesting. So the games, the ELO rating and the different games. I'm not too sure what this new Go and these must have been in previous attempts. I should have had a look what those were. But what's interesting is on the far left is raw network. So now what this is saying is, imagine if we didn't run search anymore. We just took the policy network and we said, don't explore the tree of possible moves and try and look ahead, basically remove all look ahead and just execute the network. What should I do? This is the distribution of good moves, select a good move and play. And there it is, quite a bit lower than AlphaGo 0.
Almost as good as fan.
So, yeah, almost as good as fan, but I mean, like, there's quite a way off what you can get with search. So, yeah, the way I'm maybe a bit pessimistic with, yeah.
Can you explain raw again?
So raw, remember there's like, I'm in this state, I ask my policy, what is a good move? And I use that information to guide which moves I explore down the tree. Now this is saying,
no look ahead.
No look ahead. I'm not even going to explore. I'm just going to listen to the network as I've trained it. And remember that was the trick that they did when they like wound this thing up. Is they listened to the network to guide the search, and then they said, that search actually produced a better thing than the network. Train up the network to try and mimic that, and then wrap it around and do it again. And now they're saying, okay, fully trained up. I don't know however long, 40 days of training, or I'm not sure what they actually did there. But it doesn't really matter, trained it up and then execute just on the network. And basically, munch, it's still very powerful in algorithms. Like a lot of computation, a lot of search actually gives you huge improvements. So it's really into that as you wish.
So was that raw network actually stabilized, or was it a period, time period?
No, that would have been a fully trained up. So say that blue graph that I saw, right at the top there, best performing thing. We take that network straight out of that machine, and we say play, but no longer allowed to do any look ahead via Monte Carlo tree search.
How much computing power or hardware does it need to just implement the raw network?
I'm not sure. I mean, I imagine the pass-through is not too much.
Yeah, but the training is you still need to train it.
And the search as well.
So that part's the
Training.
same. But
Just
you exclude the search. So search is expensive, could be expensive.
Yeah.
8-bit my phone.
Yeah. Yeah.
And then, yeah, so the point I kind of want to make is just, I mean, this thing is kind of shown in a lot of articles as a big breakthrough in deep learning, which is sort of the deep residual network that they've trained up. But I mean, they're still doing a huge amount of search, which Monte Carlo tree search has been used for many years on these kind of games with discrete states and determinism and the rest of it. So it is amazing. I definitely wouldn't have thought of it. And yeah, it only applies to a set of games. So yeah, I guess those are my comments. Anyway, now we can play the demo if it works.
Okay. Who knows Connect 4? Who doesn't know Connect 4? Okay, so maybe quickly explain.
Which question did you
Explain. Connect 4.
Yeah, so this is the game of Connect 4. I'll probably also play 2.5 games of Connect 4.
Easy to understand?
But each player has a color, so we're going to have actually, I don't have color visualization at all, so we're going to have like crosses and circles, 8 by 6, and you play, and as you can see, they actually slide down the slot. So at the beginning, you only can play anywhere in the first row, and then after that, your options are only like to stack on top or play basically where there's gravity, things fall.
What
you
is
take
the
turns, and the diagonal, you want to get 4 in a row, either vertically, horizontally, or as illustrated, the diagonal also constitutes a win. You get diagonal 4 in a row. Okay, so it's going to take a little bit of like audience participation, but here's
I'll
the
help to
labeling
collect
of the
votes.
moves.
Okay.
This is the labeling of the moves. So we've got a choice now. We can either play. So there's actually there's a first row. It doesn't show us our options, but we have options of 35 to 41, including. So
36. So we can pick in one, 36.
So, should we take 36?
The 36, there we go.
Yeah, 36. Any objections to 36?
You don't have to vote. I think the voting starts after this.
Once we lose a win.
Okay, so there we play.
Let's see if we can beat this thing.
Okay, so it played over here. Okay, so something.
I don't see the probability. Well, there's probability. Maybe you should just show the value. Is that the value network? This is a Python notebook.
Does it give us some support as well?
No,
we have to guess.
we have to guess.
So this is kind of the distribution here. All of these numbers here sum to 1. These are all the possible moves. So this is the output of the entire thing, the network plus the search.
Is that our suggestion there?
No, that is AlphaZero.
So
AlphaZero.
we play there.
AlphaZero.
AlphaZero is given this distribution to the things. So one thing should be mentioned. I didn't actually play this for particularly long. Which is
Give us a
why-
hint.
Maybe we have a chance.
Okay, but the board is below. So that is just indication. So if you move it up slightly, there we go. It's giving the possible moves.
So we played. I did have a board here. If somebody wants to come and draw it on there as we play, so people can see. But if this is
29, you want to draw? Okay, yeah.
29.
Okay, so yeah,
I think only the blue pen works.
blue pen. Yeah, do everything with blue pen. Make it circle. Alright, that's it. Yeah, you can make it bring it in. That's it.
29.
Yeah, because it's just the distribution over moves. So it's like saying if you draw a random number from a Gaussian distribution, you're not going to get the mean. You're going to get some number. Actually, probably not going to get the mean.
So really, we like that position of 0, 1, 3 because that's not the highest.
No, it's not taking the peak of that distribution.
38.
So how?
It's just saying if it drew like a lot, like if it drew 100 draws, then whatever
Initial combination.
then like most of them would have been actually the far left.
Then why does it choose?
I guess it doesn't have a random thing saying.
Yeah.
What
Pick
made it
random.
subject?
No,
It's a randomized initial selection.
yeah, because it's drawing from a distribution. It's drawing a random number
Oh, randomly from that distribution.
from that distribution. Yeah, so if you did a lot of trials, then you would see that it peaks on where it wants to pick, but it's not always going to pick there.
Does it use a softmax?
38.
35.
Okay, so we need 4. Okay.
So we say
Where do you play?
Play 0.
Like 39.
X and 0, the other way around.
Maybe it's the other way around. Maybe just change it down.
37. It's going to win. 37.
37. What is 37? 37? Yeah, 37.
37.
Yeah.
Winning move.
Yeah, that's a winning move. 37 is a winning move. This thing is not trained well. It can't work.
I guess I should have let it run a little longer. Okay, so what do we need to win?
Give it a chance.
39. Beat the computer, man. Beat the computer.
30 was really good.
We won.
Okay, 22. What?
22 we win. 22 we win.
Okay, now we go.
No, sorry, we didn't see his previous move.
39.
So no,
It's the previous move.
no, we didn't see his move. He blocked it.
He didn't.
He blocked it in the leg.
Yeah, no, not in the previous one.
No, you hit the wrong one.
We played the other one.
You played there and not there.
No, sorry, that's right. Use the arrow.
39. For the win. It's cheating.
So we won. Okay, so no, I should have made this a little more user-friendly, but we won.
You won.
Yeah. So
And it cheated, isn't it? It's supposed to be the next step.
it's just going to play another game. I think it's wanting like a
rematch.
A rematch. Yeah. So I mean, just pick 30.
37.
38. 38.
This is just to feel that you must want to feel good. We don't train it that much.
Okay, now let's get the power moves. Okay, now 36. 36.
26. No, wait. We should do our own.
38.
36. It needs 2 more moves.
36, yes.
19. I think the probabilities are very
I'm actually 39.
Okay, so 26, just to be can.
We're gonna try.
Okay, so we must go to 13 days.
24.
24.
Get in the middle there.
No, you can't do it.
These are the possible moves here.
We've locked it.
30.
No, we wanted 30.
Yeah, now we've got.
It's playing a little bit better.
41.
We've blocked it, yeah. Okay, go.
Yes, sure. 34. You're well behind on your marking.
25. 25.
Yes, we've got
That's one first. 25.
Okay, 25. It looks like.
Yes. 27.
25. You got two off the middle there.
27. Okay, what do you got? 27. Okay, 27. 27.
Learning what's doing as well.
27. 35.
There's no
He's trying for that.
Yeah, so he's going to win. He's going for it. We have to play. We lost.
We won.
No.
There, you see? Straight up.
Yeah, but who's moving? We won.
We got 4.
Well, we've been twice. It's maybe because we're so many. Clearly not trained enough.
But for interest, how long did you train?
Hey, sorry?
How long did you train?
Yeah, I like to train.
It only trained for.
There's not a GPUs or anything.
No, it was just on like a.
An Azure?
On Azure, but like a.
How long did you train?
CPU. I trained it from this morning, maybe like. Actually, in time, I'm not sure.
But how many iterations did it train?
I think it was like 13. What they were calling games, and then there was like. So it first builds up like a memory map of stuff that it uses, and then it trained it. I don't know. It's probably like total number of games. It's maybe like 60,000, I think. Something like that. Yeah, I can't
That's
remember how
small
it broke
amount
it
of
up, but I
games,
did like tournaments and then matches. Yeah.
We still say.
Yeah, we still say. But for sure it's not going to be running very fast on what I was running. Yeah.
So how many moves are there in this game? What are the
Yep.
moves for?
Sorry, code just quickly.
Yeah,
we'll make it available on
so
the website as well.
Actually, that's a very important thing. is this slide here. Longer. Yeah, so like none of this is mine. I'm just more like a sounding board of what I've played with. The code repository is there, either in our Cortex Logic GitHub account, we forked the original repo, otherwise it's in one of these articles.
The Medium one.
I think in that Medium article is the link to the original
With some descriptions.
original work, which is also a link from somebody else's work, as open source stuff goes. Yeah.
Your Python notebook is just got a trained neural network in it for you.
Yeah.
Yeah. So you can actually train it further. So use the weights and everything, the code, everything is there. So yeah.
It's actually quite user friendly, and also they've done it quite well where you can just basically write your own game rules and swap out that game.py file, and you should be able to play tic-tac-toe or any other game that you decide to do. There's actually quite a lot of them if you search for them. Yeah.
So chess, because the starting moves isn't completely symmetrical, does that not affect the policies?
Yeah, it does have an effect on the neural network. So with Go, where things are symmetrical and stuff, they were able to do like a bunch of tricks on the neural network side of things. Whereas AlphaZero, they couldn't do that. So it doesn't require like symmetrical moves. Also, like for chess, castling is
So the only optimization, I mean, for the policy network, I mean, it's just so minimal, the difference doesn't matter?
I think when you're encoding the rules, I'm not sure how they did the board state for the chess game. So that's another thing that also, so you've taken rules and then you've created like a board state. So for these guys, they put like another layer with 1 and 0s to indicate whose turn it was. They did 8 boards deep, maybe they should have done 12. So like all of those things are like, are you giving it just the pure rules, or are you giving it actually like a human feature? But I mean, I think that's pretty honest to just give it 8 boards deep. But I don't know how they encoded the chess board. Then I didn't actually look it up. Yeah.
Good. Any questions? Anything more? So let's. Thank you very much for. That was good. Yes, go for it.
Yeah.
We're going to go into open discussion to talk a little bit more. So yes.
A question about like there's this idea of you put in the rules and then you like let it do its thing and then you ask it the answer. In a larger scheme of things, it can come out with answers that, like if you ask it who are the poor people in South Africa, it's going to decide that it's going to make decisions that we don't like, okay, because it's just looking at the basics of it. So we're not looking at its decision process. Okay, how does that bode for the future?
Yeah, I mean,
that beautiful question to lead the open discussion.
I just think of neural networks. I mean, I must say I've played with very simple ones that I've coded myself, but that's like very, very simple stuff. Otherwise, I've done the classic thing of cloning other people's work and just running it through. But so from my perspective, neural networks is just a mapping function. And so you're training the mapping up and you're training it on data. So facial recognition, that have that kind of problem where the data set is mildly biased to like some group of people, and then obviously another group of people might not get recognized as quickly or accurately, or the age might not be determined as well, or these sorts of things, because it's really just a bias in the data that definitely comes through. So I'm not too sure from your example what the raw data would be, but if there is a bias there or something that we don't like, then yeah, it will be there in the output.
Just quickly, in terms of I think there's quite a bit of research being done on interpretability of even deep reinforcement learning and stuff. At the moment, there's research also talking about deep probabilistic neural nets as well, so that you can actually get more information out of that. What we've done in the past, for instance, as well, when you do what-if scenario analysis or causal and sensitivity analysis on these input-output mappings, you can actually try and figure out what are the factors contributing to certain outputs or the sensitivity. You can perturb some of these features and inputs, and you can, in that way, also get some information. So it becomes a little bit less than a black box, or like a grey box.
Yeah, but that will be limited to small neural nets.
Yeah. But I'm just saying as an example. Sorry, you said that? Okay, yeah, that's true. But there's quite a bit of work that's been done on these deeper stuff as well. But it's still a challenge. We want it more interpretable. Well, it's like a human brain. How do we make those? Okay, we can at least try and explain, but we can't always explain it. So, but it's. But I think we're going to make some progress there in terms of that, because that's going to become very important.
Are we trying to explain in the heuristics or the methodology that we know when neural networks actually don't explain things in that way? So we're actually trying to apply a method of deduction in a process which isn't coming to that using that process of deduction. So
that's a good.
That's why I really like this thing, is we're not using the network
no
anything more than just to improve like the policy which we're still doing search. I think that's the way. I mean, if I was to use a neural network in a big project, I would also probably not rely on it to do the sort of higher order thinking kind of things, because my just my gut feel is that it isn't going to get there. But it's really good at the one phase of it, which was coming up with a better mapping of board to move. But I can still use this search for look ahead to make a better strategy.
There's two types of neural network things happening here. One is a sort of combinatoric sort of genetic algorithm thing, finding the root, and the other one is actually training the neural network on weightings, which is independent of that. So you kind of got your rule set defined by the one side doing an algorithm, and the other side actually doing weighting. Two independent methodologies of the people. The combinatoric search, that's pretty well understood. And the other one, which is actually being generated, isn't doing the same logic, isn't working in the same way.
Yeah. Yes.
So in this example, to actually code almost like a rule of what's a rule of the game, that you have to have like 4 stacks that's either horizontal or vertical. How do you just start off with actually encoding those rules so that you can learn from that, because that's like a starting point, it's like a frame that you have to set. So
yeah, if you source code up.
Sorry?
See, but he wants to know the DSL that they coded there. What did you put in there for the Connect 4? And you see the rule set.
Yeah.
Yeah.
Can you show the Python with the rules?
We go to Python.
I'm just saying the worst part about data on AI is training it on people's comments and trolls network. That's the largest data source out there.
Oh, that is huge.
Yeah.
And the beauty is we've got the techniques to work with unstructured data. You can look at sentiment, all of it as well. Yeah, so this is the game.python.
So I'm not sure what. I haven't actually looked at this.
That's just the game stuff.
So that's the list of all winning moves.
Yeah, so this game's pretty simple. So
Allowed actions.
So these are like combinations of wins, I guess. And that's pretty easy to map out.
And then allowed actions.
And then allowed actions. Yeah. So there we go. Take action. And then there's like allowed actions.
Allowed is just the top. More.
Figure out what's possible.
I think that is just looking at this.
Yeah, so this is how you can find whatever it's called.
So it is quite hard coded to set up.
In this example, I mean, the guys that did Go, they got like really good. I'm sure they would have very smart ways of doing stuff. Yeah, there's kind of like papers and high-level stuff, and then there's people in the back room munch and like looking at lines of code and doing really. I mean, every piece of software is really good engineers
But
behind
the
it.
reason why I'm asking this is that if you want to apply this like to a business solution, because for anything to make a proper decision, you need to understand the framework in which you operate.
Absolutely.
The
What is all the possible
rules.
moves potentially?
And if you can't explain it well enough, your answer is going to
Right.
be
Yeah.
meaningless. It's
Right.
going to rise. So how do you cross that bridge? Are you relying on someone to have hard code these rules correctly, or can it actually
No,
is it smart enough to almost follow
But doesn't this only count for perfect knowledge in order?
So yeah, so in that opening slide where I said like what games you can do this, basically you need to be able to build out that search tree, and then you need the discrete state and the deterministic
so for your
qualities of the game.
state to define that you have to.
Whereas like in a business
in
case,
this
I don't know what-
example, the rules have been like physically hard coded, and that's
Yeah.
like a prerequisite.
Yeah, I mean either hard coded or you can.
I mean,
If you give a business case scenario, a cutting schedule on a piece of wood. So you would basically have your algorithm searching ahead on which ones combine to cut on a piece of wood, and then you could work out the wastage as your weighting function, and then recut, and you get a whole lot of these different cutting schedules, and your neural network would be training on that predictive layer of what would be the best cuts.
Exactly.
On that piece of wood.
Yeah.
He's pretty much answered. Do you have some examples? Because most of what you've described are very, very finite, discrete examples where you can define all the rules, but
Yeah.
the real world doesn't run by normal rules.
So you have to define a rule.
But you have to define it. Now, I think this is where it's going to be really interesting, because I think there are subsets of problems that you can maybe bring where you can, if you solve this little thing here, you've got a whole solution around this. You can maybe have another one here, another one here. A combination of stuff might solve a bigger, interesting problem as well. Because a lot of stuff, how do you eat an elephant? But you can break it down in little pieces. That might be an interim way of solving bigger world, kind of real world kind of problems. But I think the challenge is the engineering. This whole thing around AlphaZero, you can see there's a lot of engineering happening. It's smart, using the best of neural nets in terms of certain things there with Monte Carlo search. In a clever way. It's very specific, the way you look at your rules. The chess one, is it available as well?
No, not in this.
Yes. You can just, but I haven't seen practical application. I think it's up to us to.
Giving you, trying to develop this environment, using this methodology for scheduling. Also, time scheduling events, knowing what your parameters and the impacts of your different factors are, and then so instead of doing, as I said, a genetic algorithm search for this, is doing that in parallel with a neural network that you train. So the game rules are basically this combinatoric situation which you can define in any generalized case, and then actually supplying neural network to that to learn. So instead of generating all these genetic algorithms to determine what your best observation or whatever you're doing now, what the best is to do, you actually not train up the neural network and you don't have to do all these deep searches all the time.
Exactly, but that's AlphaZero. So that's the beauty of that. So because the problem is always data and stuff. Do you have enough representative data and stuff? But you just generate as many as you like, much as you like. Yeah. And it's exactly, that's why we need humans here.
I saw there was a recent thing where they looked at retinal scans for determining whether you're susceptible to diabetes, and it worked. So they looked at historical information as to whether these people succumbed to diabetes or not, or whether they eventually got diabetes, and they had retinal scans of them. So now they can just do a retinal scan and they can decide whether you're susceptible to diabetes. There's no algorithms, no computer code, there's nothing like that.
It's amazing.
Another topic, so it might be interesting to, so with this it's the competitive training that you referred to,
Yeah.
it might be interesting to know whether the same would work for a game of poker in which bluffing plays a role. Because arguably, this thing will never bluff. It will, and in poker, actually there's value in bluffing.
Well, in Go, I'm sure there's like sort of strategies it's been reported. I didn't look into the Go example other than reading the like end of the papers. But there are where basically what they said is they said, well, they looked at humans and they looked at like their play strategies, and they've got a bunch of names for these game strategies, and you kind of see how the algorithm, it starts to play them, it starts to learn. Like let's say it plays them often, it plays them every single game, it plays this kind of configuration in the corner of a Go board, and then it starts dying off and it comes up with its own strategies. And I don't know if those are bluffing in the sense of that.
It could be
the game is perfect information. It's not really a bluffable scenario in all these games. But it definitely comes up with strategies that, like in chess, you kind of play a move like.
That's right.
Could
be a bluffing
hope that
move.
They don't see something intentional, how you sort of charging up the board or something like that. So it definitely comes up with those kind of strategies. And because of the search, it's definitely coming up with look-ahead strategies and things like that. Yeah. So it was quite interesting how for these kind of masters, they looked and they saw like, oh yeah, we know this pattern of play a lot. This is a blah 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 played for thousands of years or hundreds of years. But then AlphaGo actually started petering out on some of those patterns and said, actually, it's come up with a better strategy. If you're in the corner, don't play like the classic formation, play something else, which apparently for the comments made from those players was quite enlightening for them. They dedicate their lives to playing this game with a rich history, and now there's something that's kind of showing them another few strategies which might have taken years for humans to have discovered. So that's also quite a cool thing, I think in itself.
I wonder if they found it depressing.
Yeah, it's quite amazing how it's scalability in a sense.
Yeah.
It's actually generally quite amazing.
Yeah, I think so.
It's a bigger picture. Just think about the knowledge increasing.
I think I like it, but I'm not sure if the masters would like it.
Do you think they can win again the masters?
Yes, it's going to. No, I think it's.
I don't think so. I think
it must be too difficult.
Yeah, I don't know how to empirically beat those ELO ratings, but if there's a gap of 200 or something, then it's like if you play 100 games, you're going to win them 80 times out of 100, and the ELO ratings show between the players and the current state of the art programs is just huge. I don't think we're going to catch up again.
Were those ELO ratings against itself, or was it ELO ratings against
human
ratings?
ELO ratings across the board. It's kind of in squash, you kind of have your league rating. If you beat the guy at the top, you kind of get pushed up a little bit.
That petering off is sort of human capacity.
Yeah, so this is playing a bunch of games.
Against human...
No,
against itself.
Against itself, yeah.
So that's basically partly to say that is a peak of performance.
Yeah.
And a human theoretically could get that.
You might be play up there, I don't know where.
But this is just 40 days. So if he trains for a year...
But it's still stabilized.
AlphaGo Lee was
Lee is
the top human, I guess. I think he took one game off AlphaGo Lee at the time. Yeah.
The grand goal here is to reach the AGI, the artificial general intelligence, right? And that first we beat AlphaGo, and then we get AlphaZero, which is a little more generalizable, etc. So I would see that the next step from here is then to introduce imperfect information, right? It's not deterministic anymore. So is this? Can we introduce imperfect information into this system? Or do we have to build something completely new? Is what's the way to take care?
If they could, they would have done it.
I suspect you're going to have to leave the search approach a bit. I think you'll still have neural networks in there because they do such a great job of like, I mean, like they do, they just collapse a whole search into something that can match the inputs to outputs.
They have to reinvent back propagation. The way you train has to be consistently.
Maybe, but there is a.
But that is just learning the input-output mapping. Will that constrain you in certain ways?
But I mean, back propagation is it's not natural. There's nothing that trains that learns like that.
No, but.
So if we can find a better way.
For sure.
And weights in the sense that maybe more related.
And backpropagation is
from front to back.
Yeah. Backpropagation is always, you got to have something. That's why you need to have targets. So we need to generate those targets, or that's what we're doing effectively, value and policy. Then you can use backprop. It does a pretty good job. But you're right. I think you will see new developments, research, especially if you look at unsupervised learning. Even the way the human brain works, there's not a lot of very specific targets being generated always. So this stuff is very dependent on those targets being generated.
The brain also learns in one go, basically, at a time.
Yeah.
You learn very quickly.
Yeah, it's one-shot learning stuff. But I think one shouldn't underestimate all those building blocks. You think it's one shot, but there's a lot of stuff. So I doubt that thing. Yeah.
But I think in the training, there's a breakthrough there. You get to more generalized.
Oh yeah.
So you can train back propagate in some sense with imperfect information.
Imperfect information is just variation with probabilities. Your imperfect information is just variation in the probabilities.
I think inevitably you just have no information whatsoever. There are black spots in inputs.
If I look at scheduling and I'm worried about the wind, I don't know what the wind conditions are going to do. But it's a variation. It's a variation of the probability for me to do something into some undefined poker condition. It's a variation on the probability.
Yeah.
I can't get it perfect because you can never. That you know that it's a higher probability that this condition may happen. Then you're training around those unknowns, which have a variation.
Well, yeah, absolutely. I think
so a good field to like Google keywords to put it is like Bayesian statistics. So basically the broad brushstrokes in the Bayesian sense is like anything that you don't know about, you just put a distribution over it. So if you know absolutely nothing, maybe you just put a uniform distribution over it. And then there's ways of building up these models, like probabilistic graphical models, in which you can perform inference, and you can basically, there's either connected models or unconnected, and you can iterate through, and as you get more information, you can feed it in. It's a really powerful framework for dealing with uncertainties. But it's not really the machine learning approach, although there is some overlap that people are looking into. It's a good way, a good approach. When you don't know, just put a distribution over it and then include it. You know it has some effect. The wind has some effect. I don't know what it's going to do, but it's going to be between this range, and I'll put some distribution there, and I'll try and let it feed into my decision process. So that's I think that's where it's going. It's much harder, I think.
One of the examples that we're currently busy with a customer is around hospital exception management, where initially you don't know enough information, but you've got to say you're using probabilistic graphical models, PGMs for instance, and based on that information you make decisions, recommendations, but as you get more information, you start bringing that into the mix as well. But it's also as you build this PGMs, it's also, you talk about winged or whatever, but you've got all those components there. But there could be a situation where you don't know what it is at all. And so I think there's also various levels of imperfect information. The state is not only determined by these 6 factors, it's maybe 10 other ones as well. So how do you cater for those types of scenarios?
Every time you bring in more data, you're putting a weighting on it. You're putting another factor into your models. You better put a weighting on it. You're putting in more data to your
So with these probabilistic models,
you can actually add nodes to it.
I did them in my masters for tracking aircraft, and nice about them is that I know that my state like caused my observation. So you can put, if you know for a fact you've got causal relations, which sometimes you do know. So it all boils down to really like engineering, super general. You kind of get a problem, and then you do know some information, and you can actually, if you can in these models, put some causal relationships. That also helps. So if let's say you do know that wind does influence the time of your output or something good, then that's actually kind of powerful to use, even if you don't know anything about wind other than like it's between 0 and 30 meters per second. Very unlikely it's going to be 30, something like this. You can still say, well, I've got wind into account. And then if you really want to be smart, you can say, well, wind at this time of year. And kind of just like by pulling a few things, you've kind of incorporated something that's quite a lot better than no information. Yeah.
Okay, yeah, that's right. So we can maybe take a discussion there. There's some drinks. Thanks very much for your time and everything. It's good. There are some snacks, so go for it. Enjoy.